Alright, so hi guys. This week's lecture is going to be the first of a series of lectures on neural networks. And this lecture is specifically going to be focused on the perceptron, which is sort of the most basic fundamental unit that all neural networks are made up of. So let's get started. And before I go on, I just want to say that all the images and examples in this lecture are actually from previous TJ lectures, specifically the 2019 version of this lecture. You can find the PDF of it on the website. And this lecture was authored by Nikhil Sardana and modified by Vinay Baip. Okay, let's talk about what is a perceptron. As I mentioned before, the perceptron is basically the most fundamental unit of a neural network, right? A neural network is basically a bunch of perceptrons glued together. Um, and these neural networks can learn complex functions, right? So what a perceptron does is it takes in some sort of numerical input, right? And it can take any number of these inputs. In this picture, we have two numerical inputs coming in. These are x1 and x2. And what the perceptron then does is multiplies each numerical input with a weight, right? Each input has its own weight. Um, and then it will sum all of the resulting products and then add a bias to this sum, right? And then so we basically take the weighted sum of all the inputs, add the bias, and then we get our sum here. And then we push this resulting sum through a step function. And basically what this does is if the resulting sum is positive, we output 1, and if it's negative, we output 0. That is what this sort of line represents here, right? And formalizing this sort of these steps in equations, um, the thing here can be written as here we're only having two inputs in the image, but you can have unlimited, right? You can have x1, x2, x3, x4, and so on. Here we're just sticking with 2 because later we're going to visualize this on the coordinate plane. But you basically multiply each component of the input with its corresponding weight, and then add the bias term, right? And then this is we write this as f of x. And then the final output of our perceptron, which is sort of this whole thing right here, is going to be 0 if this resulting sum is less than or equal to 0, or 1 if this is greater than 0. All right, so that's basically the basics of what this does. So to visualize this on the coordinate plane, using the sort of scheme that we were doing before where we have two sort of bits, x1 and x2, and then this is sort of the classification of each node. Let's say we're trying to create a perceptron that represents the AND function in computer science, right? So the AND function, if you're not already aware, it basically compares these two values, and if they are both 1, it will output 1. So here, that's not the case, right? Because these are both 0. Here, it's still not the case because this one is 0. Here, it's not the case because this one is 0. And here, it is, both of them are 1, so the output is 1. Alright, so ignoring this line here, we can basically graph this data as follows, where the white dot represents the 1, and then all the other dots represent 0. Now note here that the y-axis, or what we would normally call the y-axis, is actually the x2 axis. So here, sort of both axes on our coordinate plane represent independent variables, or features of our data, right? This is sort of like one feature of our data, and this is another feature of our data. You might be used to like seeing a dependent variable on this graph, on this axis, right? But that's not the case here. Both of these are features of our data. And then the color of each dot actually represents the value of the data point. Okay, so make sure that makes sense. So if we're trying to create a perceptron, we can just draw this line here. And this line seems to, do a good job in separating all the black dots from the white dots. And this actually, if we can sort of output 1 for all the dots on this side of the graph, and then a 0 for all the dots on this side of the graph, then we basically have a perceptron that has learned the AND function. So if we get the equation of this line, the equation is simply x2 equals negative x1 plus 1.5. And this is just of the form y equals mx plus b, where m is negative 1, b is 1.5, and even though we just replace y with x2, right? Because that's what it is on the graph. We don't have a y-axis here, we have an x2 axis. So rearranging this in the form that we saw earlier, we can get it into this form right here. And we get x1 plus x2 plus negative 1.5 equals 0. And this was the previous form that we were talking about, right? So we can see that W1 is 1, W2 is 1, and then the bias term is negative 1.5. And any point that's sort of on this side of the line, if we plug it into this equation here, where x1 is the x1 coordinate and x2 is the x2 coordinate, any point on this side of the graph will actually result in an fx value that's greater than 0. And any point that's less than, any point that's on this side of the graph will result in an fx value that is less than 0. And so if we then apply the step function that we were talking about earlier, which is denoted here, any point that resides on this side of the graph will be classified as 1, and any point here will be 0, right? And so by finding these weights, the W1, the W2, and then the bias term, we basically were able to create a perceptron that is able to represent the AND function. Okay. But, you may be asking, okay, that's cool, but how can we actually learn these weights, right? I mean, if we, we kind of came up with these weights ourselves, but how can we learn these automatically? So given one perceptron and trying to find the weights, what we can do, this is sort of the version of the learning rule for if we have 2 inputs, but it can easily be extended to multiple inputs. But we have the desired output of the node that we're trying to classify. It's either like 1 or 0. We have the current output of our perceptron, which is denoted as y. And then we have the coordinates I1 and I2, which represent the coordinates of the current data point that we're looking at. And so we can just apply this learning rule here, where we set W1 to equal the previous value of W1 plus the desired output minus the current output times the current coordinate that's misclassified. And then we also multiply this thing called an alpha term or a learning rate. And I'll talk more about what that is used for soon. And we sort of apply a very similar, sort of scheme to the W2. For B, it's a bit different in that we don't use any of the coordinate values, but this is basically the learning rule. And if you had multiple inputs, then you can imagine, you do W3 equals W3 plus, this whole term here times I3, where I3 is sort of like the x3 coordinate of our point that we misclassified. And something to note here is that, if the desired output equals the current output, then we don't end up adding anything because this term that I'm, hovering my mouse over goes to 0, right? So all of this becomes 0. So we only update the weights and bias term if we misclassify a point. I'm not going to go into exactly why this works. I mean, it may be obvious to you, but I've linked a good blog post explaining this, the sort of general version of the learning rule, and why the general version works in the description. So be sure to check that out if you're interested. Okay, but going through a quick example, let's say we have this data. This doesn't represent uh, like anything specific per se, but let's say we're just trying to classify this data perfectly. And this is the state of our perceptron now, right? This is the line that's represented by this equation here. And we basically are almost there. We need to get this one, though. This one is on the wrong side. This point is on the wrong side of this line. If we can kind of move this line over this way, then we are successfully classify every single point in our graph here. And so since the only point is at 1, 0, we only applied the learning rule to that point. Okay, so this is sort of the current state, the current line here that is represented by this line. And so, just simply applying this rule, we get, with the alpha value of 0.2, the desired value here is 1, right, because it's a white dot, so the desired value is 1, sorry, here, but it's actually on the wrong side of the graph, right? If it's on this side of the graph, our network is basically predicting 0, so our current output is 0. And then the x1 coordinate here, or I1, is 1. So just plugging this in, we get W1 equals 1.2. So we increased W1 here, because here it was previously 1, and now it's 1.2. And we just follow a similar procedure for both W2 and B, and then we get this new line, 1.2x1 plus 1.0x2 minus 1.3 equals 0. And we can see that compared to this line here, this line is somewhat closer to classifying this point correctly. And so since we haven't converged yet, or since we haven't classified every single point correctly, we just apply the same learning rule again, except now we use the new W1 weights here. So doing it again, we just repeat the same process for the only misclassified point, which is 1, 0, and then doing this whole thing again, we get 1.4x1 plus 1.0x2 minus 1.1 equals 0. And that, this was the line that we got on the previous iteration, and then this is the line that we get now. And so now we've successfully classified every single point in our data set. And so since we've done that, we stop. We've perfectly sort of learned our data set. One thing to note is that the perceptron learning algorithm doesn't result in the sort of optimal line that separates the data points. You can imagine that a better line would have been drawn like this, where it's sort of farther away from this point here, right? This is like pretty close. So that's sort of a disadvantage here. As soon as we get everything correct, we stop, and we don't go on, even though there might be better solutions that sort of reflect the structure of the data. All right, and so going back to the reason why we have this alpha value here, you can imagine that if this was our original line, and this was like 20, for example, then our new line could be like way off the mark. It could, instead of just nudging it a little bit in this direction, it could move so far that it actually goes and misclassifies this point. We're moving in the right direction, but we move too much in that direction if the alpha value is too large. And so even though we move in the right direction, we can actually make our perceptron worse at classifying our data if we have an alpha value that's too high. On the other hand, if the alpha value is too low, then our increments, our improvements to the line here will be very incremental, so we'll end up taking a long time. So in order to get the best results, you have to do a little bit of experimentation. The thing called learning rate is also used in neural networks, and it's also something that it's called a hyperparameter, which is something that the user specifies before training that affects training performance, and it's usually something that you have to experiment with. But just remember that setting alpha value too low will lead to like a long training time, and then setting an alpha value too high will lead to you may not ever converge because you'll always keep getting worse. Okay. Um, oh, and one other thing to note is that we start off the W1s and W2s. If we were trying to like classify some data, usually you just randomly start off with some values, and then you apply this learning algorithm. Here we sort of started off with 1.5, and that was already pretty close, but it might be like very far off. Your initial values for W, all your weights and biases might be much farther off. Okay, so non-linearly separable data. This is sort of when you can't draw a line that gets all of your points on one side of the line, right? So here in this graph, there's no way you can draw a single line that that gets all of the white dots on one side and all of the black dots on the other side, right? You need two lines in order to sort of draw the region in which all the black dots reside. And so with a single perceptron, there's no way you can actually do this, because what a perceptron is just a line that all the points on one side of the line will be classified as 1, and all the points on the other side of the line will be classified as 0. So there's no way you can sort of train a perceptron to correctly classify all of these, every single point here. So in order to solve this, we actually used several perceptrons. By using several perceptrons, what we do is we essentially draw two lines, and then using the resulting values from the perceptrons that sort of represent these two lines, we can then use another perceptron, so a total of 3 perceptrons, to classify these points as 0 and these points as 1. So this is basically what our multi-layer perceptron is going to look like for solving this problem. We're going to have these two initial perceptrons in like the first layer that represent the two lines that separate our values, right? And then we're going to combine the outputs from those two perceptrons to basically and feed those outputs to a third perceptron, which is then going to sort of look at, okay, what is this line saying and what is this line saying, and it's going to make a final decision as to whether or not our point should be classified as 1 or 0. Right? And just note that I haven't drawn the sort of bias terms that are sort of also involved in these calculations, but just know that they are there. Okay, so let's first talk about the first two perceptrons in our network that are going to help us solve this problem. These are our points just graphed on this graph again, and so this line and this line we're going to represent with two perceptrons, and the first perceptron represents the top line and the second perceptron represents the bottom line, and these are these are very simple sort of equations here, but we're just setting different y-intercepts for this graph here. The y-intercept would be positive 1.5. It's positive because you can imagine that the full equation would be x1 plus x2 minus 1.5 equals 0, right? And so rearranging those terms in the form of y equals mx plus b, you'd get, positive 1.5 here and positive 0.5 here. So this is basically perceptron 2 will output a 1 if the point that we're looking at currently is above this line, and then it'll output it'll output 0 if something is below this line, right? And then perceptron 1 will output 0 if anything is below this line, and then it'll output 1 for anything that's above this line, right? And so here we're kind of in some tricky business here because um, it really depends on what both these perceptrons are doing um, to like determine, okay, are we doing one or zero, right? Because um, yeah, it's sort of complicated because here, it's not just dependent on one perceptron; it's dependent on two perceptrons. That's basically the point that I'm trying to make. And so how can we do this? Well, it just like it's a little bit of experimentation, just trying to see like experiment with different values and what the thresholds should be. But what I came up with was you have, so here I represent O1 and O2 as the outputs of perceptrons 1 and 2, right? And so if this is our equation here, we end up getting positive values for things that are outside this sort of region, and a negative value for the stuff that's inside this region. And then once you put this through the step function, anything that's positive is going to be 0.5, and anything that's negative is going to be negative 0.5. And this is not like the only equation. There's like a bunch. You can basically uh, find different numbers, and it's quite easy to do that. This is just what I sort of came up with first, and we're going to see why this works on the next slide. Okay, so let's walk through the calculations with the weights and biases that we found. Right, so um, just remember that we also have to consider the step function here. All these calculations are just for the h values, and then if this value is positive, the final output of our perceptron will be 1, and then if h is negative, um, then we're gonna output 0, right? So let's go ahead and do this. If we plug in 1, 1, so what this represents here, O1 and O2, as I mentioned before, are the outputs of Perceptron 1 and Perceptron 2 respectively. And just to repeat, um, if sorry, if a point is above like the line for Perceptron 1, then O1 will be 1, and otherwise it will be 0. And then if a point is above Perceptron two's line, then O2 will be 1, otherwise it'll be 0, right? So doing the calculations for the function for this point here, we can see that it's above both threshold lines here, right? So both O1 and O2 will actually be 1. So when we carry out, this computation, we get 1 minus 1 plus 0.5, which ends up being 0.5, right? All right. For these two lines, we can see that it's below the threshold line that is represented by perceptron 1, but it's actually above the line represented by perceptron 2. So O1 will be 0 and O2 will be 1. And so plugging this in, we get 1 times 0 minus 1 plus 0.5, and this ends up being negative 0.5. And then here, since we are below both lines, both O1 and O2 will actually be 0. And so we're going to get 1 times 0 minus 1 times 0 plus 0.5, which ends up being 0.5. And you can see that these are like desired, we have the desired signs on all these values, right? Because here, since it's positive, we're going to be outputting a 1. Here, since it's negative, we're going to be outputting a 0. And then here, since we're positive again, we're going to be outputting a 1. And if we look at the truth table, that's exactly what we want to have. So, we coming up with these values is sort of like an experimentation thing. I mean, you can kind of use you can use logic to basically deduce like, okay, what do I want to happen, and then sort of go from there with the like experiment with different values. Um, for me, it took like some trial and error, but it is kind of fun, a fun puzzle to like come up with these values. I mean, it's not too difficult. And on the PDF that hopefully you guys should have, there are some more example problems that you can work through yourself, and then try to come up with the weights and biases for a whole perceptron. But going back to sort of learning algorithm that we sort of wrote out in the previous slide, um, so for a multi-layer perceptron network, the learning algorithm like doesn't really apply. Um, the learning algorithm was specifically for like a 1 unit perceptron. We're going to be talking more about different sort of learning algorithms when we get to neural networks. But for the sake of multi-layer perceptrons, you should just know that we can use it to represent, a non-linearly separable functions or data sets. But don't worry too much about how to automatically generate the weights and biases. Okay, so next lecture, we're going to be moving on from perceptrons to talk about neurons. And the main difference here is that perceptrons use the sort of the activation known as a step function, where if something is negative, we output a 0, and when something is positive, we output a 1. But neurons have more complex activation functions that basically allow us to learn far more complex functions, like you know basically there's many different activation functions, and the nonlinearity of these activation functions allows us to learn more complex patterns. And so that's what we're going to be talking about next week. And we're also going to be talking about linking multiple neurons together to form neural networks. Um, so that's it. Thank you for listening, and hope to see you next week or next lecture.